Okay, it's 4.4, rates of change in polynomial functions. Again, nothing new today. We're just kind of, it's a bit of a review on what we've already learned previously. This time, taking what we've learned about average and instantaneous rates of change and just applying them to polynomial functions. All right, so we have a graph here about Canada's population growth. He obtained the data online and using graphing software to create the following graph and fit a curve to the data. So, it's difficult to see, but there's the function right here. Looks quite complex, but again, it's just constants in front of the cubic variable, a squared variable, and then just a regular variable. So, pretty typical what we've been dealing with, just we have some decimal places, so no need to be alarmed. Selecting tools to determine what was Canada's population growing faster in 1997 or 2005. Who can tell me that right away just by looking at the graph? When was it growing faster? Hands up, Lyndon. Yeah.
It was growing faster 2020, around between 1980 to 2020.
Okay. The question is between 97 and 2005. When was it growing faster?
Right there. Oh.
Can you answer that just by looking at the graph? Somebody? Yeah.
2005.
Yeah, 2005, right? We know that because it's an exponential function, and we can see that the graph is turning upwards, right? So one way we can think of it is kind of the instantaneous rate of change at those years. So if I were to go to 1997, it would be somewhere around here and draw a tangent. And then if I would go to 2005 and draw a tangent, what I would notice is that tangent in 2005 is quite a bit steeper, which would represent a faster rate of change. Okay, but we're going to prove that now algebraically. Any questions so far? So all we've done is we've taken a table of values, they created a scatter plot, they drew a curve of best fit, and now we're trying to determine which has a faster growth rate or instantaneous rate of change in 1997 or 2005. So we use our formula for average rate of change. This is actually closer to our instantaneous rate of change formula, right? Average rate of change would be, I think this is instantaneous rate of change. Yeah. Because the question reads, estimate the instantaneous rate of change. And this is our difference quotient formula. So this is our instantaneous rate of change formula, where h is a really small value. So there, our a value is the point of interest. We're looking at 1997, so we're adding 0.01. So we're taking this value, 1997.01, and we're substituting it in for each value of t over here. Okay, so that would go in for t there. So it would be 1997.01 cubed negative 0.003445 times that plus 21.415 t, which is 1997.01 squared, da 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 da. Okay, and then minus that same substitution of 1997 in for t, all over 0.01. Any questions there, what we've done? It seems complex or complicated, but you know, a calculator does all that tricky math for us, and we get two values, one minus the other, over 0.01. Okay, and we end up with 362. Okay, we do the same thing now, but for the year 2005 here, adding the same value of h, and we get 373. So what does it tell us? It tells us that, in fact, in 2005, the rate of change, the instantaneous rate of change, is greater than the rate of change in 1997. Okay, nothing new or difficult about that. Any questions? Okay.
So for the x, you plugged in the 1997.01.
Yes.
On the equation, right?
Yes.
Okay.
Yeah, that's what I was doing here, right? I was doing that right here. It's not x, it's t, right? T is the x variable.
Then what do you do with the minus P 1997?
Then you plug in 1997 for t into this equation.
Okay.
Okay. So wherever you see t, you plug in 1997. Wherever you see t, you plug in 1997.01. Okay.
So what? Repeat that again.
So this is what you're plugging in for the t variable, 1997.01, which I did here, right? So it's all of that minus the same thing where you have 1997 now cubed.
Oh, gotcha.
Okay? All over 0.01. You're just taking this value and plugging it in for t, and then you're taking this value and plugging it in for t and subtracting them. Okay? Any other questions there? Alright, so that's the algebraic method. That would be the method that I would ask you guys to use. Here's the graphing strategy. So all they do is they plug it into a graphing calculator. You guys should have your graphing app on your phones. You plug in this long equation right here into your phone. You'll get a graph, and then they look at the curve of the tangent line. Okay, so we know that's the instantaneous rate of change. So they go to 1997, they take a line that's tangent at that point, right there at 1997.
Sorry to bother you, sir.
Please excuse the interruption.